Before we dive into the topic of quantum computing, we need to discuss classical computations. We know that any classical computation can be done in binary. So we fix our binary alphabet 0 and 1, and any function that we compute can be considered as a function with n-bit input and k-bit output. Right? So this set Bn, so this is the set of binary strings of length n, or n-bit expressions. So the output here is k-bit strings. And so this could be numbers or text. We know that any text can be encoded in ASCII and converted to binary strings. Or this could be the state of a computer screen, because after all, computer screen is rendered as a finite set of pixels, and the color of each pixel is encoded with, say, 24 bits, something like this. And so then any computable function can be thought as a function with n-bit input and k-bit output. We can go even one step further and consider, instead of a single function with k-bit output, the array of k functions, where the function fi computes ith bit of output of f. And so this means that now each function fi is a function with n-bit input and a single bit output. So the output is 0 or 1. And so now we're going to focus for now our attention to functions of this form. So we'll look at functions with inputs that are binary strings of length n, and output is a single bit. Now the basic theorem here is the following. So any function f from Bn to B may be expressed as a composition of elementary functions and or and not. Now let us review these elementary logical functions. So we have x and y. So here we can construct the value table. So we take so x could have values 0 and 1. So y could have values 0 and 1. And so here we interpret 1 as true and 0 as false. And now x and y means that x and y is true. So this means that for this function, the true value 1 is assumed when both x and y are equal to 1, and its value 0 elsewhere. So this is the value table for the n function. So for the function x or y, so this function says that that either x or y or both are true. So the value table for this function is well known. So it's true everywhere except the case when both x and y are equal to 0. And finally, we have the function not x. So this is negation, right? So if we have x here, then not x has the opposite value. So if x is 0, not x is 1. And if x is 1, then not x is 0. So let us consider the following example. So let's look at addition of 3-bit integers. So suppose we have two 3-bit integers, so where we denote the bits of the first integer x1, x2, x3, plus another 3-bit integer y1, y2, y3. So a 3-bit integer represents a number between 0 and 7. So when we add two such numbers, then the maximum result is 14, which is a 4-bit integer. So this means that for the output, we need to have 4 bits. And so here, so this would be an example of a function from B6 to B4, right? So the input is a binary string of 6 bits, and the output is a binary string of 4 bits. Or, so this can be alternatively, so this is the same as 4 functions from B6 to B. So here we will compute each of the z bits separately. So as an example of this calculation, so we can take 1, 1, 0 plus 0, 1, 1, right? So what is this? So this is 6 plus 3. So the result is should be 9, and 9 is 1, 0, 0, 1, right? So this is an example of this calculation. Now let us look at the last bit Z4. So how do we calculate the Z4 bit? So the last bit indicates the parity of a number. So if Z4 is equal to 0, then this means that the number is even. And if Z4 is equal to 1, then the number is odd. And we know that the parity of the sum is determined by the parities of the summands. So this means that Z4 depends only on the values of x3 and y3. And so we have that Z4 is equal to 1 if and only if, right? These two summands have opposite parities, right? So to get an odd sum, we need to have one summand must be even and another must be odd. So this means that here we will have that x3 is 0 and y3 is 1, or we must have x3 must be 1 and y3 must be 0. We will be using the following short annotations for these operations. So for AND, we will use this symbol, and for OR, we'll use this symbol. So this will be X or Y. And for NOT, we're going to use this symbol, right? So then the Z4 can be expressed as a function of x3 and y3 in the following way. So it's not x3 and y3. So this assumes value 1 when x3 is 0 and y3 is 1. So this corresponds to this case. Or we have x3 and not y3. So this is how we can express the function that represents the last bit Z4, right? So this is like F4 function, as a composition of AND, OR, and NOT, right? And so in this course, we will also be using circuits in this course. So let us draw a circuit for this function. So here we have the x3 input and y3 input. So let's consider two branches, and let's put a negation here. So here we put a NOT gate. And so we also split this and put a NOT gate here. Right, so this is for this negation, we will need this NOT. And so for this piece, we have NOT x3 and y3. So here we're going to put the AND gate. And also we need to put an AND gate on this another pair. Right, so we have this. And we put another AND gate here. And finally, on the outputs of these two ANDs, we put an OR gate. And so this will be the output, will be our Z4. So this is the circuit that represents this Boolean function. And so this is a computational scheme for computing the Z4 bit of this sum. Next, let us look at the computation of Z3 bit. So to compute Z3 bit, we need to know the values of x2, x3, y2, and y3. So Z3 is a function of 4 bits of the input. Let's make a table for the values of Z3 bit. So here is the value table for the bit Z3 depending on the values of x2, x3, y2, and y3. So for example, if we look here, right, so x2 and x3 are 0, 1, so this represents 1. And here y2 and y3 are 1, 1, so this represents a 3. So 1 plus 3, that's 4. But 4 is 1, 0, 0. And the second last bit is equal to 0. So this means that the value of Z3 is equal to 0 here. Now, let us look at the following row of this value table. Right. So here, so we must obtain value 1 when x2 is 0, x3 is 0, y2 is 1, and y3 is 0. So how can we achieve this? So we can form the following expression. So let's form not x2 and not x3 and y2 and not y3. Right? So we can see that this expression will have value 1 precisely on this input, right? So this can only be 1 when x2 is 0, x3 is 0, y2 is 1, and y3 is 0. And so this expression will generate value 1 in this line of the value table and zeros elsewhere. Now, if we look at the next row here, so to generate value 1 here, we could take expression not x2 and not x3 and y2 and y3. So now, if we have values 0, 0, 1, 1, then it's only in this case that where this expression will generate value 1. And now we put the disjunction or between these two things. Now, this expression will generate value 1 precisely in two cases. When we have this row of the value table or the next one. And now we do this for each row of this value table where we have value 1 for Z3. So for example, for this one, so we take not x2 and x3 and not y2 and y3. So this conjunction will correspond precisely to this row of the value table, and it will generate 1 on this input. And we put disjunctions of conjunctions that corresponds to each row where we have 1. So for example, here we have not x2 and x3 and y2 and not y3. Right? So now we took care of these 4 entries where we have 1. Or, so the next entry is we have x2 and not x3 and not y2 and not y3. Or, so this entry we have x2 and not x3 and not y2 and y3. Then for this row we have x2 and x3 and not y2 and not y3. Or, so finally, for the last one, we have x2 and x3 and y2 and y3. And so what we see is this function. So this will be the function that calculates Z3, right? So this function will have values 1 in the correct rows of this value table, and it will have value 0 in all other rows. So this means that the value table for this function is exactly the same as the value table for Z3. So this means that this function represents Z3 function, right? And so what we were able to achieve here is we have shown that we can take the function Z3, right? So this is a function from, well, in this case, from B4 to B, right? And we can write it, we can express this function as a composition of elementary logical functions, and, or, and not, right? So here what we have is a composition of the 3 elementary logical functions. So what we see is that this method works for any Boolean function. So if we have a function from Bn to B, then we can always use this strategy and find an expression of any Boolean functions in terms of a composition of elementary logical functions. So this is this presentation of a Boolean function is called disjunctive normal form. And basically, any Boolean function has a disjunctive normal form, and this proves our theorem that every Boolean function can be written as a composition of elementary Boolean functions. Now let us talk about complexity of computation here. So we know that we can write 2 computer programs that will perform exactly the same task only one will work fast and another will be slow. So what's the difference here? So at this level, so we can say that a function may have many different representations as a composition of elementary logical gates. At this level, we can say that a Boolean function may have many different implementations as a composition of elementary logical gates. In this example, for the computation of Z4, we used 5 gates. In this example of the disjunctive normal form for Z3, if we count, so here we used 47 gates. So for a general, so if we have disjunctive normal form from Bn to B, right, so then roughly, so we have about 2 to the power n conjunctive terms, because the number of rows, so if we have n Boolean inputs, then the number of rows in this table is 2 to the power n. And each conjunction has n terms. So roughly, so the complexity of a disjunctive normal form is n times 2 to the power n. Right? So this is how many elementary logical gates we need to use to represent an arbitrary function on n bits, right? So using disjunctive normal form. Now, this gives us exponential complexity, and this is pretty bad. And so this means that the advantage of disjunctive normal form, that it is universal, so that any function, so it gives us a theoretical statement that any function can be expressed as a composition of elementary Boolean functions. But in practice, this implementation is often inefficient, and we can often create better implementations of functions. Now, let us recall, what is the textbook method for adding integers? When we add integers, we use the method of a carry. So suppose we need to add 1, 0, 1 and 1, 1, 1. So how do we do that? So we start with the lowest bits. So 1 plus 1 is equal to 2. So we write a 0 and we have a carry of 1. Then here we have 1 plus 0 plus 1. That's again 2. So we write 0 and we have a carry of 1. 1 plus 1 plus 1. So this is 1. And we have a carry of 1. So, and we get the answer, right? So this answer represents, well, 8 plus 4. So this is 12, right? And here we have 5 plus 7. And so it is 12. So this is the addition of 5 plus 7 done in binary. In this method, we use 2 elementary operations. One is addition mod 2, and the second is a carry. Well, addition mod 2 is actually implemented here. So this, when we compute the value of Z4 using X3 and Y3, this is nothing but addition of X3 and Y3 mod 2. So what we can do is we can take this scheme and we can just denote it by plus, right? So this is addition mod 2. Right, so we have 2 bits of input and 1 bit of output. Now, the computation of a carry is very easy, right? So when do we have a carry? When we add 2 bits. So we have a carry only when both of these are equal to 1. So this means that carry is just the AND gate. So now we can design a circuit for the computation of Z3. So here we have X3 and Y3. So first what we do is we calculate, so these are the last bits of our integers. First we need to decide whether we have a carry or not. So this will be the AND gate on these 2 inputs. And now we have also x2 and y2. And what we need is, now we need to do addition mod 2 of three things: x2, y2, and the carry. So what we can do is we can put a plus gate, right? So which is given here. And then we need to put another plus gate here, right? And so this will give us the computation of Z3. So here we calculate the carry from the previous bit, right? And so then to calculate the value of bit Z3, we need to add mod 2, the carry, and the two bits x2 and y2. And now what we can see is that for the plus, we are using 5 gates, right? So this means that for this computational scheme that computes Z3, we are using only 11 gates. So which is way better than 47 gates that were given by disjunctive normal form. So now we see the distinction between the concept of a function, of a boolean function, and the concept of an algorithm. A boolean function is a function from n-bit strings to a single-bit strings. And an algorithm is an implementation of this function as a composition of elementary logical functions. And here we had two examples of two algorithms for computing the value of Z3. One example with disjunctive normal form, which was essentially a table lookup. And the second function is more efficient computation of Z3 using the idea of a carry. This point of view defines the complexity of an algorithm. So here we can say that the complexity of an algorithm is the number of elementary logical gates that we use in implementation of this algorithm. So for disjunctive normal form, the complexity is, well, typically it's n times 2 to the power n, but there could be other algorithms for computing exact same function that are much more efficient. Efficiency of algorithmic representations of Boolean functions is clearly, practically a very important problem. So let me give you as an exercise the following task. Design logical circuits for functions Z1 and Z2 in our example of addition of 3-bit integers.